Alright, thanks for joining me here. This is my first attempt at a video that is going to try to bring you up to speed on some of the reactions that we need to know to be successful in this biochemistry course. The first one is esterification reactions. Those are condensations of acids and alcohols, and they generate a water molecule, and that's why they're called condensation reactions. And so I'm going to try to go through several of these sort of basic chemical reactions so that we can get a good handle on the chemistry that is required for success in this course. So we're going to start here with an acid, carboxylic acid. Okay, so these are organic acids, and they're the first reactant in an ester reaction. And you notice I'm showing you non-bonded electron pairs here as dashes. Some of the organic chemistry people will write the 2 dots in there. That is one way to do this, but it's slow. And so whenever I write a dash like this, that's representative of 2 electrons. And if it's in between 2 atoms, like between this C and this O, then that's a bonded, those are covalently bonded electrons, 2 electrons being shared between that oxygen and that carbon. In this case, that's a non-bonded electron pair, but it's useful to keep track of because we can count the charge on the molecule and so forth and so on. Okay, so there's your organic acid, and then we're going to react this with a second molecule, which is our alcohol. This oxygen also has 2 non-bonded electron pairs on it, and these 2 molecules are going to react to form an ester. Now, choosing what part of the molecule actually reacts has to do with what kind of attractive forces are on these atoms. When you look at this carbonyl carbon, you can see that it's bonded, double bonded to an oxygen here and single bonded to an oxygen there. Oxygen has very high electronegativity compared to carbon or hydrogen. Carbon and hydrogen are pretty similar in their affinity for electrons, and oxygen has a much higher affinity. So what that's going to do is it's going to pull electrons away from this carbon, the carbonyl bond here, the carboxylic acid carbon, and it's going to make it slightly positive, and these oxygens are going to be slightly negative in terms of their polarity. So what we've got here is a situation where we have a slightly positive carbonyl carbon and we have a slightly negative oxygen on this alcohol. And so what can happen is that that oxygen on the alcohol can actually attack the carbonyl carbon. It's called a nucleophilic attack because that negative charge is loving the nucleus of this carbon, the positiveness of this carbon, and that'll try to form a bond here. Okay, the electrons for the bonds are going to come from one of these non-bonded electron pairs, and it's going to try to add a bond to this carbon. But this carbon already has 4 bonds, so if you add a bond here, you have to take away a bond here and move a pair of electrons up to that oxygen. Remember that carbon can never make more than 4 bonds with anything because it only has 4 electrons in its valence shell. And so that oxygen of the alcohol is going to add to the carbonyl carbon, and we're going to generate an intermediate that looks like this. And now that oxygen is going to have 3 non-bonded electron pairs on it because we moved one of the double bond pairs up into that, and that's going to give it 2, 4, 6, 7 electrons for its share of that paired electron there. 7 of those belong nominally to the oxygen, and so that generates a negative charge on this oxygen. Okay, we still have the OH of the carboxylic acid, but now we've got a new situation here where the alcohol has donated one of its non-bonded electrons to make this bond right here, and we still have the hydrogen bonded there, and the R rest of the alcohol. And so if we count these electrons that are this oxygen share, we have 2 there in the non-bonded pair, 3, 4, 5. That's actually 1 electron short of being neutral. And so this oxygen is positive. Okay? And we can think about this and look at this intermediate here, and we can say, if I just deprotonate that proton there, I can satisfy this positive charge here, and I do have a place for that proton to go, and that's right on this OH of the original carboxylic acid. So that brings us to a second intermediate. We have this R, and we haven't done anything to this O yet, so it's still in its negative charged form. And what we've done here on that original alcohol is we've taken these bonded electron pair from the hydrogen to the oxygen. We've taken the proton off and left the electron behind, and that makes this bond right here. And so now we have this neutral alcohol group without its proton bonded to that carbon. And now we have a very similar situation. We have this original OH of the carboxylic acid, but now it has a positive charge because it's accepted that proton, and one of these free non-bonded electron pairs is now sharing with that H+, and that makes this group have a positive charge. So what can we do to eliminate that positive charge here? Well, one of the things we can do is just eliminate this completely as water, H2O. If we take those 2 electrons here, we're going to satisfy that positive charge. It's going to move the positive charge over to that carbon, and we'll get this intermediate. Okay, and that's going to look like this. R, C, still got the O up here, and that still has its negative charge. This water is gone, and now we're left with the portion from the alcohol. But you can see now that this carbon is 1 electron short, so that's a actual positive intermediate here. You can see that because there's 2, 4, 6 shared electrons, so 3 of them belong to the carbon. It needs 4 electrons and added into its valence shell to give it neutrality here, and it only has 3, so that's positive. And how can we get that back? We can just move that electron pair down into a double bond with that carbon, and we generate our ester. Okay, and this is in neutral form. There's no charge on it. This is our ester, condensation product of an acid and an alcohol. And of course, we eliminated a water over here. And so to make this complete reaction, we can just have our water as a product. Okay, so that's the esterification of a carboxylic acid and an alcohol in general form, and that's the mechanism you can think about. We can also hydrolyze this ester by attacking it with water, so we can generate an intermediate just like this. That proton can then go and protonate the alcoholic oxygen and generate this intermediate, and then we can eliminate that alcohol and regenerate the carboxylic acid and the starting alcohol. So that would be the hydrolysis of an ester. So these mechanisms are reversible. You see all the arrows here are pointing both ways. And that's essentially how you make lipids. That's how you make a lot of different esters in biochemistry. The acid here that I chose to show you this with is a carboxylic acid, so it's an organic compound. It's an organic acid. You could just as easily do the same chemistry with phosphoric acid, and if you did that, then you would have a phosphoric acid ester instead of a carboxylic acid ester. Phosphoric acid esters are found very commonly in DNA and RNA and nucleotides, and so that's another aspect of this general reaction. Well, I hope you've learned something here. I know for some of you this is probably really basic, but for others I hope that it will be useful for you. You should know how to do this type of reaction mechanism. If you do know how to do this, it's going to help you a lot. Okay, thanks for tuning in.